Modern theoretical physics remains fractured. Despite their individual successes, quantum field theory and general relativity are mathematically incompatible. This incompatibility stems from a shared, unexamined premise, the assumption that spacetime is a smooth, continuous manifold that remains uniform down to infinitesimal scales. When gravity is treated as a perturbative quantum field on this smooth background, the math produces uncontrollably infinite loops in the ultraviolet regime. These divergences make the theory non-renormalizable. Alternative frameworks like loop quantum gravity identify the need for discrete primitives, but they often struggle to show how these discrete structures naturally collapse into a smooth, four-dimensional classical spacetime without manual fine-tuning. This persistent mathematical failure suggests that the concept of a smooth, independent spacetime background may be the primary obstacle to a unified theory. This is where we introduce the unified dynamics framework, also known as distinction theory. In this model, spacetime is not a physical fabric. It is a statistical macroscopic effect generated by a background-independent data compression algorithm operating over a discrete network. By analyzing the topology of this network, we can derive continuous gauge symmetries, gravitational effects, and particle masses from purely combinatorial rules. We will use this framework to address the electroweak metastability crisis and calculate a mathematically rigid value for the Higgs boson mass. This suggests that the laws of physics are the macroscopic manifestation of data routing constraints within an unembedded network. The universe's scaffolding is a network of interlocking K4 simplices. These graphs have 4 vertices, 6 one-dimensional edges, and 4 two-dimensional faces. Connectivity is rigid. Every vertex maintains a degree of 3, providing exactly 3 localized pathways for information transport. The system is governed by 2 primal invariants. The first is the total configuration dimension, n equals 192, representing the network's absolute structural headroom. The second is the topological overlap deficit, delta equals 7, an irreducible geometric mismatch occurring when interlocking these units. The ratio of these 2 invariants, 7 divided by 192, defines the master scalar. This ratio dictates the scaling behavior of the substrate, fixing the ultraviolet spectral dimension to exactly 4/3 through a recursive contraction mapping. This anchors measured physical constants to discrete invariant geometric fractions. We define the vertex state update density as the volume of unexecuted computational phase data queued at any specific node. The network operates under a hard processing ceiling derived from the primal invariance, the vertex information capacity limit, exactly 7 divided by 768. An admissibility operator acts as a gate. When a node's local data density approaches that limit, the gate closes, generating topological boundary pressure. When primary edges choke, the system uses triadic co-boundary transport, forcing queued data outward across two-dimensional faces. This off-axis transport injects chiral torque. Recombining on downstream edges, the data wave misses its original phase alignment. This transport non-closure permanently traps the data wave within a self-perpetuating simplicial holonomy circuit, a localized standing wave. Mapping this circuit frequency through de Broglie emulations yields an inertial mass equivalent of approximately 35 millielectron volts. In this framework, inertial mass is an inventory backlog, data trapped in a topological loop. As the network undergoes recursive refinement, we observe the system at its topological closure boundary, known as level n equals 7. At this scale, the high-frequency microscopic anomalies undergo destructive interference across a coarse graining shell, smoothing out the jagged edges of the graph. We can then apply the Gromov-Hausdorff metric convergence theorem to the relational path costs of the network. The math proves a smooth, continuous, flat Minkowski space inevitably emerges as the macroscopic limit. This reveals a profound truth. What we perceive as macroscopic gravitational acceleration is actually just phase wave refraction. As a wave's execution velocity drops in response to local topological boundary pressure, it follows a geodesic path, creating the effect of gravity without requiring spacetime curvature. Gravity and smooth spacetime are statistical illusions that occur at the macroscopic limit of the network. This capacity-limited model also addresses the Standard Model's electrometastability crisis, the prediction that the Higgs coupling will drop below zero at high energies, leading to vacuum decay. Unified dynamics modifies the Higgs coupling beta function by incorporating the information capacity limit. While the Standard Model plunges toward zero, this calculation curves and stabilizes. The capacity limit acts as a geometric screening factor, represented by the term 1 minus 7 over 768. As energy scales flow towards the ultraviolet, this screening factor forces the beta function to freeze. This maintains the coupling above the zero threshold, mathematically guaranteeing absolute vacuum stability. We set the bare ultraviolet coupling to the invariant geometric fixed point and integrate to the infrared. The result is a mathematically rigid Higgs boson mass of 125.0 giga-electron-volts, a mass derived entirely from localized traffic limits within the discrete network. We have now derived continuous physics entirely from discrete, background-independent combinatorics. The same foundational graph structure that yields the 125.0 giga-electron-volt Higgs also derives Standard Model gauge symmetries and the Bekenstein-Hawking entropy law. This framework fits the existing collider data without requiring any free parameters or manual fine-tuning. In contrast, standard quantum field theory and general relativity rely on dozens of manually tuned inputs to maintain their predictive power. These results suggest the universe is an information-theoretic engine governed by strict computational limits. For any framework to be valid, it must provide specific, falsifiable experimental signatures. Unified dynamics makes a rigid prediction for the cosmic microwave background, a primordial tensor-to-scalar ratio of approximately 0.01765. It also predicts a scalar spectral index tilt that flows to an infrared value of 0.9685. Upcoming B-mode polarization surveys will provide the data necessary to test these exact parameters. If observatories can confirm these specific numbers, it will definitively indicate that reality is a capacity-limited discrete network.